Let's get going. So yeah, hello everybody. Welcome to today's webinar. What is LSPc? And Xometry is pleased to announce the incorporation of Nexa3D's LSPc process, launching over a dozen new materials into the Xometry Instant Quoting Engine. This hour will be jam-packed with information about the novel lubricant sublayer photo curing process, if you're wondering what LSPc stands for, and the needs it fills in the additive manufacturing landscape. So before we begin, I wanted to remind you, the audience, about the questions tab in the GoToWebinar platform. Please feel free to submit questions at any time, and we'll cover as many as we can at the end of the presentation. This event will also be recorded, and Xometry will send an email with a recording for you to rewatch and share with your colleagues. So let's just jump into some introductions. My name is Greg Paulson. I'm the Director of Applications Engineering here at Xometry. We're a digital manufacturing marketplace. And I've worked on thousands of projects professionally in over 15 years of my career in advanced manufacturing. And much of this has been in industrial additive manufacturing, but I also work in processes like machining, injection molding, sheet metal, and beyond. We offer 20 different manufacturing technologies here at Xometry. And joining me today is our guest host, Louis Sims. He's the head of product marketing for Nexa3D. Nexa3D is the OEM and inventor of the LSPc technology, and they're providing a fleet of resin printers and material offerings through Nexa. He's our subject matter expert and has over 13 years of experience across the 3D printing industry. And Louis may be a familiar face if you watched Xometry's webinar on SLS 3D printing about a year back as well. So welcome back, and awesome to have you on board today, Louis.
Yeah, glad to be here, Greg. Thank you so much for having me. And excited to introduce you guys to LSPc technology.
No, this is great, and I cannot understate. This is a jam-packed webinar. Louis and I have worked through this, and I'm just really excited to go into details about the technology, and also we're practical people, how and where to use it. You know, so the materials and so beyond the process, the materials and how they may be used. So briefly, here's our agenda. We're gonna just talk about who we are first, so we'll cover that very quickly about Xometry and Nexa3D. We also want to talk about how this technology evolved, like what its predecessors were from resin-based stereolithography moving up to LSPc. Louis will go through some case examples, and then we'll run through materials, design tips to get you jumping right in with the technology, and then resources and live Q&A. This is another reminder, any questions you have, submit them anytime with the questions tab, and we'll try to get to as many at the end of the webinar. So let me just kind of start by saying Xometry, we make a lot of parts. We are a digital manufacturing marketplace. We were founded late 2013, really started building parts for customers in 2014 and never stopped. We integrate technology right into the heart of our platform, and we serve over 30,000 active buyers. And what's unique about us as a marketplace is we're connected to suppliers as well. So we have an active supplier network of over 10,000 globally. So we both have the domestic US as well as locations in Asia and Europe. Xometry also has ThomasNet, which is a global supplier directory of over 500,000 suppliers and 76,000 product categories. So we want to be the first place you go to get something made, and we try to make that pretty firm with having this vast resource here. And we're just a full manufacturing service, so parts on demand. And we do it a little bit differently than just a single shop because we embrace the marketplace aspects. You may be familiar with this if you ever got a Lyft or a Uber for transportation, order from Amazon, or use like PayPal for payments. But this is using a marketplace aspect for manufacturing is unique. It's something that we help to invent and pioneer in the field. And what it gives you as a customer is a single place to go. That there's an app for that essentially, where you can upload, click, drag, upload, place an order. So we call that our instant quoting engine. And then we manage the supply chain, whether connecting that work with the right suppliers, assuring quality along the way. And it's not just prototype work. This could go up through spec production. So we hold the standards like ISO 9001, AS9100D for aerospace, ISO 1345 for medical device manufacturing, and also we work in ITAR and also working on CMMC, which is very exciting as we are a digital platform, and that's what ITAR will be evolving into. So we're very excited to talk about that. So this is, I could demo this during Q&A, but the Instant Quoting Engine, it's free to use. You could literally take a 3D file, upload it to Xometry.com, or access it through some of the add-ins that we have for Inventor, SolidWorks, Onshape, and Fusion 360. You get pricing and lead times. You could toggle between these manufacturing technologies, add features, finishes, change quantities, and you'll see that pricing dynamically update. And it's not a guesstimate, it's a buy it now price. So instant gratification. No more waiting for that RFQ response. It's just click and buy. So on that, like I said, I'll be very brief on the announcements because I just want to cover topics like LSPc. Lewis, let's talk about Nexa3D and go into LSPc.
Yeah, absolutely. So if you haven't heard of Nexa3D, we were founded in 2016 and have over 85 employees. We're headquartered in Ventura, California, and that's not only where we do a lot of our R&D and engineering and sales activities, but it's also where we do all of the manufacturing for our printers and auxiliary equipment as well. So we have channel partners across the globe, over 100 of them, in fact, and growing rapidly, and over 750 printers installed worldwide. But what really makes us come to work every day is building a sustainable digital supply chain through additive manufacturing. Companies like Nexa and like Xometry represent a huge opportunity to leverage additive manufacturing to not only revolutionize the way things are made, but where they're made, and doing things in a much more sustainable fashion.
Yeah, so this is a great overview because you are talking equipment materials, kind of the full kit and caboodle here. And one of the flagships of this is the LSPc technology. So I'll let you take it from here, but yeah, let's talk about where this came from.
Absolutely. So as Greg, I think, mentioned earlier, I've been in the industry for just over 13 years, the majority of which working for a service bureau like Xometry. And one of the first pieces of advice that I got when joining the additive manufacturing industry many moons ago was that when it comes to additive manufacturing, you can have a part fast, you can have it at a low cost, and you can have high quality components. And that meant repeatability, product uniformity, accuracy, and aesthetics. But what followed up next to me was honestly surprising as a young kid, and that was you can have two of the three, but not all three. You could have a part fast and get the quality one, but you're going to pay a pretty penny for it. Or you could have a low-cost part that met those quality specs, but you were going to sacrifice time. But as we look at the growth of additive manufacturing, its movement into not only prototyping, but low, mid, and now high volume production applications, we can't afford to sacrifice any of those three. And so that's what we do at Nexa, is we looked at these three aspects and said, how can we solve all three of these and deliver exactly what people need to deliver production parts with a high throughput? And in order to really understand how we got there, I'll give you guys a little bit of an overview of how far we've come as an industry, particularly as it relates to that photopolymerization. So if you look to your left with stereolithography, this was introduced in the mid-'80s by Chuck Hull and really revolutionized the prototyping industry. Utilizing a UV laser, it fired into a large vat of resin, which is where it gets the name from, and selectively cured that photoreactive resin utilizing that laser. It gave you great, beautiful, crisp, clean parts, but it wasn't exactly the fastest process. Then, almost 20 years later, we had DLP introduced, and that's what you see there in the middle. And that really turned that photopolymerization on its head, both figuratively and literally. On the literal side of things, DLP said, you can utilize a lot less resin and print a little bit faster if you turn that build plate on its head and actually build bottom up rather than top down. Now, where it really revolutionized things was transitioning from that single point where you're drawing each vector and taking all that time to projecting the entire layer all at once, utilizing DLP projection technology that you've seen in probably things like old DLP TVs or at the movies with IMAX and things like that. And the way that works is it takes that entire projection and utilizes the DLP chip to project those pixels across the full build platform all at once. Not only did that speed things up, but it also allowed us at the time to use a lot more reactive and high performance resins. And so that started unlocking things that got you away from, your grandpa's resins from the 1990s that would break if you looked at them wrong, to really robust functional materials. And now today we're sitting at the third generation of that photopolymerization, and that's MSLA, or masked stereolithography, taking a lot that we learned from the DLP process, but transitioning it into a much more accurate and scalable technology that can benefit the end user for years to come. And the way this works is you're trading out that DLP lamp and chip for an LED array that then shines UV light up through some collimating lenses to help focus and evenly distribute that light. And then it hits what we call our interface layer, which in many cases is an LCD. And so this LCD basically selectively blocks or allows light through to cure that layer all at once. And where that really succeeds is not only in controlling that process down to the true pixel level by utilizing an LCD, but it's going to provide some scalability advantages that we'll discuss here in just a moment as well. And that's what you see here in this technology comparison. So taking it back to that SLA that we just learned about with that single point laser, as I mentioned, this is slow. And the challenge there is that really makes scalability not only in size, but in the number of parts that you can produce in a certain period of time, or the throughput of the system, a little bit limited. So again, produces really nice, clean, crisp, beautiful parts due to that fine laser attribute of it, but it's very slow. And then you have a fun aspect whenever you're directing a laser on galvos or mirrors, if you will, where as you get away from the center of the build, that laser is going to oval out slightly. That's going to cause slight distortions in your part, which means that there might be issues with uniformity or accuracy in the parts that you're building on various parts of the platform. So if you look at this graphic, the part that you build on the top left corner might look a little bit different than the part that you build in the center of the platform or in the part at the top right of the platform. And so that's kind of the challenge there. Now, granted, these, depending on the printer, can be maybe more minute discrepancies or more major inaccuracies, depending on how that's deployed. Moving into DLP, you end up with a kind of the inverse of this. And essentially, when you're using a projection system, think about it like a flashlight. If you're shining a flashlight directly down, you see this beautiful, perfect circle, but then a little bit of diffusion near the edges, right? The light isn't as powerful. Now, if you were to utilize that full space, the parts that you're building in the center are going to come out beautiful, crisp, clean, perfect. And if you look at the edges, they might not be as good, whether that be like from a mechanical perspective or fully forming, things like that. And so in order to overcome that aspect, you've got to do one of two things. One is you move that projector a little bit closer and you shorten your build volume to just that solid, really crisp, clean projection point. Or you move that projector away, you leverage a little bit of that diffusion, but to gain build volume. And we see both cases in the industry today. So for many, it's going that first route, which is kind of tightening it in and honing that in on that portion of the crisp, clean area. But that limits your ability, even though it's fast, to build a higher volume of parts. And so that's what challenges that throughput and production readiness there, even though you're ending up with good parts. On the other side, as you move that projector away, you've now got scalability, but your parts might lack a little bit of the accuracy that you would see in a tighter controlled environment.
Sorry, yeah. I've seen this in the industry across, like, so not just in resins, but across different industries. When you lower the scan time per layer, like, or the time it takes to go per layer, all of a sudden you have a step change in how much your throughput is. So deliverables per day. But as you mentioned before, sometimes that's at a trade-off of accuracy. So this is really interesting because we have like a LCD pixel system where essentially that when it's active, it's black, and then it'll deactivate a cell and let the light shine through and create that create that curing effect. But it does scale on XY, so you can get really big on the platforms in theory with this, versus like multi-projectors or things where multi-laser systems where you have like weird overlap ranges and stuff, so you can have a consistent part edge to edge.
Absolutely. That part consistency edge to edge is what really matters in a high throughput environment. And as
Yeah,
you mentioned,
absolutely.
scalability comes not only in size, but in the technology itself. By leveraging LCD technology, which is innovating at an exponentially faster pace than DLP, you get to leverage enhancements like the movement from 4K to now, we have a printer at 7K. Who knows what we'll be at next year in terms of resolution and detail. And we get to leverage that as well. Now, LSPc technology in particular, you're probably wondering what makes this kind of our secret sauce or our version of MSLA technology. And not only do you have to look at the light engine itself and the imaging mask, but everything that surrounds it. So any of these inverted SLA processes are going to have a physics challenge, and that is if I move that build plate up and down too much, it's going to create what we call peel forces. And whenever those peel forces occur, you can risk delamination, part separation, membrane damage to the membrane or whatever sort of interface layer you're using, and ultimately cause a failed or damaged build. So a lot of printer manufacturers are having to slow down that process in order to accommodate for those peel forces and or change the way that they're doing build setups to better accommodate that. What we did is we said, okay, well, let's cut the problem off at the head, and that is that peel force. And so we invented a self-lubricating membrane. That's where the lubricant sublayer portion of our technology name comes from. And that allows the part to more easily slide off that interface layer, help reduce or eliminate those peel forces, and leverage the full printing speed that this technology is capable of doing.
Yeah, you have kind of a quick comparison, like a relative comparison of different build times, and this is true. Like when I talk to user operators of these platforms, unanimously they're all like, it's fast, and it does change the way that we think about throughput, because typically on a build platform, when we talk about parallel capacity, like how much can I ship to my customers a day, right? We're usually thinking fleets, which fleets are still a good thing. I'm not dismissing fleets, because for what production requirements we have, we need fleets. But what you can do as well with LSPc is you can assume multiple build trays per day versus one per day. And that means that a row of parts, and actually I'm going to move to this video here to kind of keep some momentum, a row of parts can be, made, done, and removed, tray swapped out, new run, 4 or more times a day versus, that taking over a 4-day period for one machine.
Absolutely. You're looking at the transition from printing parts in hours and days to minutes and hours at most. This is a great example while it's wrapping up. This is 2,600 pulleys printed on one printer in 23 hours and 14 minutes. So if you break that down, that's roughly 32 seconds apart. So extremely high throughput, and that's not even our fastest printing resin. So I think actually if you skip to the next slide.
Yeah, that's a click. Oh, this is the surface finish one.
Oh yeah, I wanted to highlight this as well. So again, I mentioned earlier that sacrifice of speed for quality. So I wanted to show you guys kind of what you can get out of LSPc technology while still leveraging that speed and that fast turnaround. And that is a part like you see here. With these slow curves, you would typically see some really heavy layer lines. It would look a little gnarly and maybe not the prettiest looking part. And with the fine resolution that we're able to achieve with LSPc technology and utilizing the advancements in LCD technology, you can see that you're ending up with injection mold quality aesthetics, but with the speed and turnaround and throughput of additive manufacturing.
Yeah, and something I want to highlight here as well is the previous image you saw a video, and we're going to talk about like small parts and high quality does yield production in these machines. But these machines, because they do have a more even distribution of accuracy, you can do full platforms. So this is a larger component. You can build parts like that on these machines as well. So they're kind of multitaskers on what they're able to do. So they're very versatile. I also want to point out here, because when we talk about design tips and things, we're going to be talking about support structure. That if you imagine this is built upside down, like it's coming out of the vat when it's being built. Any overhanging features do have support structures, so that's what these fine lattices are. So if you're not familiar with resin-based processes, all resin-based processes, most 3D printing does have support structure that's made of the same material that you're producing the part out of, with some exceptions in soluble support for FDM or SLS or MJF, which don't require it. And so those are removed afterwards and kind of lightly sanded or cleaned off of any residual nubs there, but it's there to hold it in place because gravity exists, and then afterwards we remove those.
Absolutely. So this is the example that I was talking about regarding throughput. So this is an example of a genericized beveled cylinder here. Didn't want to point to a specific customer geometry. So you can see here roughly 25 by 25 by 100 millimeters in size and 25 centimeters cubed in part volume. So this was built on our ST45, which is our second fastest printing material, but also really robust kind of engineering material as well. This on the Zip Pro would print an entire build just in so basically one layer of parts, not leveraging the full height of the Z-axis, which we can do that too, would do the entire build in 1 hour and 36 minutes. On that build plate, again, leveraging that scalable LCD technology, we can fit 66 parts on the XY build plane of the platform. That results in a print time of roughly 1.5 minutes per part. And if you look at multiple turnovers per day, and that's what Greg was alluding to earlier, where you can really count on getting multiple prints out per day without affecting your lead times, this results in 758 parts per day just off of one platform. To put that into perspective, utilizing other technology on a DLP printer, that would take almost 3 hours to print. You could fit a maximum of 28 parts on that XY build plane, resulting in part production of 6 minutes per part and only 178 parts per day. And that's where, again, where we look at moving into those higher volumes, you have to have that scalability. And so with the printers below, we see the Zip Pro and the NXE with very similar XY build planes, as well as our Zip, which is our desktop printer, where we distill that same industrial technology just down to a desktop format as well. So all of them very sizable build volumes in terms of throughput.
Yeah, absolutely. And something, a little fun fact I have to say, because I've used the programming software for the Nexa, essentially the time it takes to print 1 versus 66 is identical. It's so like how long does it take to print 1 on the build platform? It'd be about 1 hour and 36 minutes. So you get the bonus when you add more. You like to, so it's like a lot of additive production technologies. They like their neighbors. So yeah, let's talk about some case examples and how this may be utilized to give some inspiration, and then we'll jump into some of the materials and design tips.
Absolutely. So the first one, the one that people are most commonly turning to additive manufacturing for, and that'll feel really comfortable when it comes to production or end-use parts, is part complexity. So what happens when I design a part that is difficult to manufacture through other methods or can only be manufactured utilizing additive manufacturing? And so a great case here is with WeMed, and you can see here that as part complexity increases, traditional formative manufacturing technologies like CNC or injection molding, you see that cost per part rise exponentially because it just becomes more difficult to manufacture. Whereas when you look at additive manufacturing, as part complexity increases, that cost per part stays relatively the same because you can leverage complexity for nearly free. In this example for WeMed, they developed an internet-connected stethoscope that was deployed during the good old COVID times here to not only look at alternative, direct, fast ways to manufacture, but because they also designed a part that was unable to be manufactured in any other way. And in that case, you're looking at technological benefits justifying that cost, right? But as you look at maybe the next opportunity, you can also see that additive manufacturing is commonly turned to for a time to part. So as you look at formative manufacturing, your time to part, or how long do you have before you need the part? If you need it very quickly, the costs rise very sharply, and it takes a lot of time to get to even just that kind of first article, let alone the full volume. With additive manufacturing, you see that scale quite linearly, meaning that as the time you have and the number of parts increases at a linear fashion, you can see that managed quite well. And so in this example with Stellantis, they answered an RFP from the French police saying, we need, I believe it's 7,200 parts, and you have 3 months to design, functionally test, and manufacture these parts from start to finish. So they really, put their heads together and decided that Nexa3D Technology was the one to choose, not only for the design and functional testing aspect, looking at our material options, but also because of the speed of production. They won the bid. They delivered those 7,200 parts in under the 3-month time frame. And in fact, the contract was so successful that this contract was extended to over 18,000 parts, all produced with one printer.
Yeah, that's pretty amazing. And I think like time to part is really important here. And also, by the way, the resilience to rev change
Mm-hmm.
plays a role. So if there is a revision change, so the thing is connecting two changes, right? In formative tooling, you, especially like if you have something like this where it's a vehicle fleet, so I could still consider that lower volume production. So it's, even though it's in the thousands, it's still, it's not, we're not making 100K of these units. And that tool cost is still being amortized pretty heavily in the per part basis
Mm-hmm.
on formative tooling. So this gives a really good alternative for low volume production, as well as if you have a rev change, or if you anticipate, hey, this connects to a device that has seasons to it, think like iPhones, right? It has a new generation every year, or the PCB updates every now and then. I just change the file and I do my next printing round. Like it's just swapping files. It's not redoing tooling for that.
Exactly. And lastly, this is a great example. And this is again where people tend to shy away from additive manufacturing because it can just be so darn expensive, or the throughput isn't there to help mitigate that delivery time or the cost. And so here's a great example from Max Resolution 3D out of Germany, where they regularly print over 50,000 parts a month, accommodating order sizes of 1,000 parts plus, utilizing a robotic work cell. So they took a little bit of the labor out of it and integrated a robot to help manufacture these. And our technology is very automation friendly. So again, regularly delivering over 50,000 parts a month. And you can see here formative manufacturing, which people often turn to for higher volumes. Typically, as you produce more parts, you get to amortize that tool, which you just talked about, over a larger number of parts. And then now that cost per part is much more affordable. Additive manufacturing has historically struggled with this as we get into higher volumes. But by managing our total cost of operations and by having that higher throughput, ultimately, with that same printer, you are getting more parts out of the printer in the same amount of time, which lowers your cost per part and now allows additive manufacturing to compete well at higher volumes. And so this is really where Nexa, I think, breaks away from the pack in terms of our throughput, our output, and our production readiness.
Yeah, absolutely. And you have these different platforms, and we were talking about the build sizes for them. Something I like though, and part of like Xometry, so we're connected with suppliers who are running the Nexa platform. So when you click, drag, upload your files, and you'll get that pricing and lead time. And you can look and compare against different processes. And one of the things you'll see is as you add quantities, that scaling does happen different. Like so, SLA, for example, may become less competitive with scale because it's really good for that super low volume, where Nexa becomes more and more competitive. And so like this is kind of the power of the marketplace and what we have on our quoting engine. But the Zip and the Pro Series machines, they could run the same materials, and depending on the need, so if you are validating a model and you're doing like one or two, Zip may make the most sense for that type of run. But when you're doing full array parts, like what you showed in some of those examples, the Pro Series makes the most sense. But the good news is that essentially the parts are identical as a rebuild.
Exactly. As I mentioned earlier, we actually started with the industrial platform and said, let's take this same technology. We're not removing anything. Let's just distill this down to a desktop platform. So now you're graduating with the same technology from concept modeling and functional prototyping through to low and mid-volume productions, perhaps, and then getting into even spare parts and MRO activities on the tail end of the product lifecycle. So because you're not having to change that technology or change the way you're manufacturing or designing either, you get to leverage that technology from point A to point B and beyond pretty seamlessly.
So this is great to see like this, and this is kind of where the Nexa3D technology comes in. So your experience, like if you're looking to get some parts made through Xometry, right, you're going to be focused on the process, but the materials that you have. So this next section is highlighting the materials that we offer and kind of we have like some general groupings of them. So general, engineered, and specialized items, and then actually like come and rubber like materials. I'll put because I separate those out as well. But we did launch with over a dozen materials within this process, and each one has different strengths and attributes to it. And this is just kind of a visual gallery of some of these. But I'm going to dive in a second here and talk about how they may compare against each other as well. So let me just jump into that. So also, I'm very proud of my spider graph. So if anybody on comments wants to be like, "Wow, that's a really great chart, Greg," I mean, I'd really appreciate it. Uh,
I'd start off and say
anyways,
that's a really great chart, Greg. I
oh
love
man,
these and how this
that's
is
totally
visualized.
unsolicited. Thank you so much for that. Yeah, that's great. Uh, this is actually me trying to tackle Excel for too long of a time, getting these numbers to look somewhat straight, even though they came out crooked. But that's all I see. But anyways, so general purpose is going to be kind of your bread and butter materials that we have under the Nexa platform, the LSPc platform. Those include X45 Black, X Pro 410 Black, X Model 17 Clear, and X GPP Gray, which is actually the gray material. Is very pleasant for, especially for prototyping. That's what's imaged here. What I want to describe about and show kind of on this spider graph about the general purpose is they tend to be all rounders. Like that's the whole point of it, is their attributes are typically very good, but they may not have like the high specialty engine like that you'll find on the engineering resins. So you can see here they're HDT, which is usually something you consider when you look at end use parts with photo resin, photopolymer materials, is what type of environment it's going to be in. The HDT is fairly the same for these. Like it's right around what you'll find with other photo resins. You have some varying tensile strengths to this, where the X45 tends to have a little bit better tensile strength than these other general purpose. But if I'm working in a humid environment, I may want to consider that when choosing, because X45 does have I would say like a little bit higher water absorption at that 6% than that moisture absorption than what you find in a lot of photo resins. So it's something just to consider there. Other things we think about is tough. What does toughness mean to me, right? And that's when you think about a impact strength. So you'll find little correlations. Usually the tougher materials tend to have longer elongation, because it turns out toughness is just being able to pop back in shape afterwards. So a little bit of flexibility on the material, like what you see in X Model 17, it could be what you're looking for there. That's also our clear resin that we run in this process. Any comments on the general purpose or standard resins, Lewis?
I think you summarized it quite well. I think things I'll point out is the X Model 17 is a custom formulation that we released specifically focused on clarity. So if you've got any needs for high levels of translucency or transparency, this is a fantastic option for you. And then, as you mentioned, we've got two black options, the X45 and the X Pro 410. Relatively similar in properties, with the X45 kind of coming to the top with its tensile strength properties. But again, if you're going to look at any sort of testing in a very humid environment, or maybe like underwater testing or water tightness testing or resistance, X45 may not be the material for you, because it does have a slightly higher water absorption percentage. And then, the XGPP gray looks beautiful, makes a beautiful part, and is a great all-around resin as well.
Yeah, it's just a well-rounded. And personally, for that, I like using gray materials. I don't know why. It's just something I'm used to. But if this is the XGPP, but this is when I'm prototyping, I always kind of choose pleasant gray working through. So now this looks a little bit different, right? This chart looks a little bit different from this chart, because when we talk about engineered resins, there's purpose behind their chemistry, right? There's something beyond just let's get a shape that generally works for this. Usually they're going to have peaks. They're going to have things very specific to them that differentiate them from others. So I do have X45. So X45 is my general purpose, and you'll see it kind of in the background unoutlined, just to kind of give you a comparison of how much that difference may be between these. But you see that some of our materials now have a higher peaking of heat deflection, going up to 91 and 87 if you look at the XE and XESD in particular. So now you have a little bit more higher heat resistance. And with that, though, typically higher heat resistance, like I said, everything's related, typically means a stiffer material. So you'll see those ones that have a peak here. When you look at elongation or break, it's down to less than 8% on some of these. So just understand if you're looking for living hinges, maybe not your material for those, but we have other materials like the XPP, which behave similar to polypropylene. And in fact, its failure mode is not snap. It's just like kind of keeps on twisting. It just kind of keeps on bending. So it is a much more flexible photo resin that we have under here. Flex strength tends to have a correlation with tensile strength. So tensile is kind of how much pull, and flex is how much you can, how much it'll take to build to a deflection there. And you'll see again the stiffer materials like ESD, which is also our static dissipative specialty material, and CE tend to have that higher level of stiffness. But yeah, usually ESD is very purpose centric. I am working in an environment where I need static dissipation. So this is going to be what you'll be choosing if you're looking for that, especially in like any production or anything that's going to be fixturing through. If you're trying to simulate that ABS, the ABS 3843 has a great black color to it as it's being printed, and really can help mimic what you see with injection molding. And mentioning that the polypropylene materials, again, that is, if you do have living hinges or you need flexibility or pliability within your design, that'll be something that you lean into. And now to see more peaks here. So I have this, now moving to this specialty resin. And in this particular thing, this particular graph, I'm highlighting the high temp resins, which is really unique for photo resins. Because usually the downside is no matter what you engineer in a photo resin, you end up having a lower HDT than just a typical thermoplastic. In this case, and you can see X45 again as a reference, general purpose compared to these huge triangles that you're seeing on these properties for X-Peak and X-Ceramic. And again, these are photopolymers, but they've been formulated with very high stiffness, which means don't try to break them or don't try to flex them. They will chip on you. But the HDT of 280 Celsius and 238 respectively for these two materials is huge in this industry. In fact, actually, if I compare that to I think 213 for cyanide ester on carbon DLS, and I think you were in like the 200s area for Ultim 1010, which is our high heat deflection thermoplastic in FDM. These actually surpass those in chemistry, which is really interesting.
Yeah, absolutely. And on the X ceramic, highly rigid, high ceramic filled resin, I do want to point out there, anytime you mention ceramic, there's kind of two forms of ceramic when it comes to additive manufacturing. You could do like a secondary ceramic where you build the green part, you fire it, and you end up with a solid ceramic part. That is not this resin. This one is really leveraging ceramic and those benefits to add that rigidity, that smoothness, and ultimately that high heat deflection that you mentioned.
Yeah, absolutely. And I'll channel Tommy Lynch, who's one of our senior application engineers in additive at Xometry. When you think flexibility, though, don't think plastic, think toilet bowl, think porcelain on these. So I do want to make sure that when you're building these, if you look at these designs here, like these are actually designs for blow molding. They're much thicker, much more robust. They have kind of self-supporting, self-strengthening features to it. So when you're working in those environments, just know that any flex can lead to a break. So it's very different than like the polypropylene, where its chemistry is to flex, but you do get that high heat deflection. So very good for tooling inserts and other jigs and other high heat applications. But just be mindful of that in your design stage.
Absolutely.
Yeah. And the last materials I want to highlight is we have three variations of rubber-like materials. So ranging from Shore A44, which is the X-Flex 475 black, to 55 with the white variation of that. And then X-Flex 402 has a Shore A73. And when we talk about Shore A values, I'm talking about squishiness of a part. So if you think chewing gum is about a Shore 20, rubber band's going to hit you right around a Shore 50, and then car tire is about a Shore 95. So those kind of range that kind of rubber band to like a little bit firmer feel on the print. And what's unique about these is usually a photopolymer rubber-like material squishes well, but then its responsiveness, so that energy return, and its elongation, not too great. So its responsiveness. I'm going to knock on PolyJet for a section. Kind of feels like, almost like a fruit roll-up level responsiveness, and then the elongation. You'll always stretch it until it tears on you. Essentially, is kind of how you're like, how much does it stretch, and then it'll tear on you. Where these materials are much robust, they have a much like elongations from 150 to 230%, and the energy return is really important. And I think that's a marvel in photo resins that I've seen recently is a much more responsive material. So that's when we're seeing those grips, those insoles, those paddings are being created with these processes.
Exactly. These are really robust elastomeric resins that have incredible performance. I was hoping to have some samples here to show you, but the shipping carrier not to be named has failed me. But you could twist, you could attempt to tear, and good luck with that. You could use these as gaskets and seals and things like that. It's a really robust resin. So not like historical elastomers you may have seen just from a few years past.
Yep, absolutely. So it's just cool to see this evolution, and there has been a photopolymer evolution. Like when I started in the industry 15 years ago, we were only using SLA for a one-day check with understanding that it will chip or break on us. And so now to see the material chemistries hit what I consider like end-use stable, that's pretty exciting. There's still a lot to go compared to sometimes injection molded thermoplastic and stuff, just because they've had a lot of science, and I don't know, there's like 300,000 variations available, in an open global market. So there's work to be done, but it's still very, very exciting. So on that, we talk about how this technology increases throughput, gives part-to-part accuracy, and tends to benefit, parts in a low volume production environment. So I can't make one-offs, but I start to see more economic benefits as well when I'm building that, building a lot run with this. We have different engineered materials depending on what your application is, and we offer over a dozen. And to get you a jump start, this is really a broad overview of design tips, but I do want to talk a little bit about designing for this process. And it's good news is it's very similar to a lot of designing for DLP type systems in general, just because that's how this technology kind of works. But one of the things you need to understand is that it is drawing your part out of a liquid resin bath, so it's held upside down. Whenever we're talking about angles, we're talking about kind of, if you imagine the part upside down, those angles there, and and everything we're thinking about is, will it grow, and will that feature need supporting structure? Will the supporting structure battle the feature? Like, I don't want the supporting structure to win. I want the part to win when I'm snapping off the supports, right? So thin walls, thin geometries, and also things like, will it create suction or vacuum as it's building? So for example, an upside down cup. So let's just talk a little bit about what that may look like in practical terms. We don't need to go over every single one of these, and actually we have these design tips as well on Xometry.com. But the big things I want to talk about is recommended versus achievable. You need to know the rules and then know how you could break them. And that's the same with design tips. I do recommend, as you're designing, looking at the recommended as a minimum. And then when you're building and you need that feature to be in that achievable, you can move up to that achievable in your design. We do need to think about how that material can be cleared of liquid resin. So this is coming out of liquid bath. If my hole diameter is too narrowly elongated and blind at the end, you have literally forces that are holding that liquid in the very end of that blind hole that can be difficult to clear. And when these resins go through a UV bake, so essentially afterwards, they go through a curing stage in ultraviolet, any trapped material will solidify. So when we think about blind hole depth, that 3x hole diameter recommendation is not just about resolution, but it's about clearability. In a standard production environment, will this hole clear out naturally with our standard process for cleaning? Through holes, obviously, I got another hole on the side, right? So I could clear out a lot more, a lot easier, so I could do a different aspect ratio. And now when we talk about resolution and achievable vertical holes, we have different vertical hole diameter. So if the projector is going up and down in that Z direction, 0.8 millimeters is our recommended or higher, but it can go down to 0.3 millimeters. But just understand some of those rules apply for that aspect ratio. And on the non-vertical holes, you do have a little bit of a different, you want to be a little bit more broad. So that's anything that's going to be growing on the side of your parts. So side features make them a little bit larger. And Louis, I got a question for you. So you have different design rules for opaque versus clear resins. Do you want to kind of clarify why that may be?
Yeah, for any sort of particularly full layer cure technology like DLP or LSPc, and you're looking at exposing that entire layer all at once in a clear resin, you're going to have what they call kind of a cure through, which is it's a lot easier for that light to penetrate kind of through that layer you're curing into the next layer above it. So you want to make sure and just kind of accommodate for that. So it's fairly easy to overcome just as long as you're taking that into account with your design from the very beginning. And I think that these design tips that you have here are really helpful in that regard.
Yeah, the cure through can also kind of make your holes look a little like oblong if you go too small in that. But yeah, that's and even in like heat-based systems, like I'm a powder bed fusion person, and in heat-based things, you always want to kind of create a keep away zone as well, because the same thing happens thermally, right? If a hole is too small, the heat on one side of the hole is reflecting on the other side of the hole, and essentially it will just fuse the trapped material inside, and so you don't have a hole anymore. So this is why we have these design tips. Wall thickness. Wall thickness is the #1 reason why our team may call you with DFM feedback on any additive process. So heed our words well. But keep your walls between 1 to 5 millimeters. You don't need to go too thick on this. Think injection molding design. So instead of adding thickness to create a more robust feature, add ribs. That's going to be add ribs or self-support reinforcing design shapes like C's, T's, and O's. If you look vertical on those, think of that. Think of that as a piece of paper in a C shape, kind of holds up. If it's an I shape, flops to the side. That's kind of your design. Some design tips when you think about design for resin and most additive processes. And also, if you do have the need for ribs, we're looking at potentially a 25:1 rib spacing, the wall thickness ratio. So whatever that, if I had a supporting rib here, holding this up, based on the wall thickness, that's a good guideline for how many ribs, like what the spacing of ribs you need to help support that feature. But this is something just to understand. There is such thing as minimum wall thicknesses. There are design achievable or like machine achievable things, and you'll see any OEM will talk about the detail achievable. But in general, when you aim for the minimums, it's similar to rules that I always say this, like of going to Advanced Auto Parts and asking for the thinnest brakes possible. You're introducing risk into that decision. So by keeping within these wall thickness guidelines, you're going to have much more consistent part, both on the output as well as expectations. And also, you may not get a call from our case management team when we see a DFM flag on it, because we do check your designs afterwards and make sure things print smoothly. So on that note, we're talking about unsupported angles. And do you want to go over kind of like what are some of these rules here, Louis?
Yeah, so anytime you're looking at unsupported angles in an additive process that utilizes support structures, there's going to be some basic things that you want to keep in mind. The first is, as Greg mentioned, there's recommended and then there's achievable. When it comes to an unsupported angle, you're certainly looking at maybe the achievable of 30 degrees minimum for an overhang, but probably recommended best first time print success to make that around 45 degrees without any challenges. And then as you look at the kind of span bridging example that you see over to the top center portion of this print, which is our lovely X-Rook, you can see that you're going to want to kind of stick to a kind of 25-to-1 ratio to span a wall thickness and make that self-supporting. And if it's unsupported, you want to make sure that that span is going to be under 5 mils to ensure that it comes out and builds correctly. Similarly, unsupported overhangs that you might have in your design, you want to recommended to keep those under 2 mils. Again, you're always welcome to push the technology, but with that, you assume a little bit of risk regarding the printability, and you'll probably get a call from Greg's team of experts.
We do our best, believe it or not. We actually have decades and decades experience in additive manufacturing. But so we know, like I said, we know when to break the rules or when to push the system. But I'll tell you this: typically in a design stage, if you're doing low volumes, we let more get away. But say all of a sudden you want to make 150 or 1,000 of these units, we're going to take a deep dive to mitigate any requirements that require support, as well as make sure that anything that may affect build consistency, we're tackling. And because we want you to be happy with the product you receive, and one of these things with these production things is we want consistent results. So it's the same thing in machining. Like if you have a thin wall, we'll slow down the machine. We'll make that feature achievable. But if you're moving to a production of 300, we may ask to thicken that up because it will drive costs and will drive risk into the part.
Absolutely. And this example here with that X-Rook shows you that even following those guidelines, what you can achieve with that process. That entire rook is built unsupported. So everything from the hand features to the overhangs to your diamond mesh, all of that was designed appropriately according to these design guidelines, and you're able to execute quite smoothly and repeatable for that component.
Yeah, absolutely. And again, the good news is knowing these design rules, if you embrace these, you now know the design rules for like half our additive processes. So this is what's good about this is that they do transfer over. The last thing is just text and features. So what is text? Text is spans. Text is unsupported overhangs. So you're going to find that very similar rules apply there. Text is thin walls. So emboss or engrave, you want that line width to be at least 0.5 millimeter. I recommend, if I'm embossing or engraving like about, at least 0.4 millimeters. I recommend about 0.5 millimeter either direction. Tends to look really crisp and clean. And character height needs to be at least 4 millimeters tall. sans serif is preferred. So something like Arial versus Garamond on your design, because they have those little serifs turn into infinite edges that can cause a inconsistency in what it'll look part to part in print. And my last tip here is draft. So if you are making any text, and I commonly do this whenever I'm building text into my designs, is adding like a 3, 4, 5 degree draft, whatever kind of looks good in CAD. But it allows you to have crisper features superficially, but what that draft's doing is also creating a wider root, a wider base into that part, and it actually helps mitigate some of those unsupported overhang requirements because you have that angle that's giving you a little extra boost. So if you're at if you're right at a 5 degree draft and you're on a 25 degree angle, you may get into that 30 degree range in your design. So that's just like something that I do regularly when I'm designing and building in text. But adding draft can help beef up your features without losing detail. So this is a great time. And by the way, I'm super excited, Louis, because I see a bunch of questions here. So I think we're going to jump into this in about a minute. But please submit more questions, and we're going to spend 5, and we may run over like maybe 10 minutes talking through them. But I really want to recommend everything we're talking about too, including this webinar, will be recorded and posted on Xometry.com. We have fantastic guides on every single technology, every single process that we offer. So Xometry.com, if you go to our resources page or you go to our solutions page, you can find a whole page on LSPc. with guidance, tools, and tips. Materials, data sheets, you can name it. So those pages are excellent, excellent resources, as well as we have a lot of videos and information that help kind of compare how different technologies respond in different environments. Our Will It series, I call it edutainment. It's fun. It's me breaking parts in different ways across different processes. And it's kind of the benefit of having, 9 different additive manufacturing processes is being able to compare those one-to-one. And as always, I know I saw some questions about pricing and comparison. Our instant quoting engine is a great place to go. Upload your CAD file. You can see pricing and lead time and compare between different technologies, see what fits best, as well as you can contact our expert engineering team to just learn a little bit more or ask a question that we can help answer. And we have a lot. I can't state this enough. We want to be the first place you go, Xometry.com, to get any thing that you're looking to be produced made. The quoting engine helps speed up and lubricate the procurement process. The diversity that we have and what auto quotes will kind of amaze you on what we offer. And we offer the whole gamut from traditional manufacturing like machining, fabrication, molding, to 9 different 3D printing processes now with the addition of LSPc. And then these higher scale processes like die casting, extrusion, and stamping. So we do offer the gamut, and we'd love to be your production partner.
Yeah, and lastly, you guys got to see kind of some of the features of the X-Rook, but if you're really excited to see, or to not just see one of these, but to hold one in your hand, feel free to go to our website, or you can scan this QR code right here, and we'll actually send you not 1, but 2 and some of our most popular resins, so that you can see this design for yourself. You can understand what you're capable of in terms of the accuracy, the features, the detail that you get from this process. So it's a really great, robust sample that we've come up with. And so we'd love for you to test it, try it out, request one, and let us know what you think, and we'll take it from there.
Yeah, absolutely. And I kept that QR here as well, Lewis, so so people aren't scrambling with their phone right now. And I also want to mention that you want to try out a new material or any of our processes. I have this this code right here, try Web 25, 2Bs, all caps. You could use that right now for $25 off your next quoted project. And here's some pictures of parts in LSPc in our little Excel. So I'm going to jump in with some Q&A and run through. And again, thank you all so much for submitting, and please keep on submitting. Even if we don't get to those questions, I'll try to follow up with you after this event. So question on the tech side, how big can this scale when you talk about the culminating lenses, and like how big of a build size do you think is achievable with the LSPc platform?
Sure. So the platform as a whole, our largest platform is 19.5 liters whenever you combine the X, Y, and Z. And whenever our next largest platform is right at 17 liters. So, and then our desktop printer is right at 8 liters. So still really sizable for the total build volume. But when you're talking about LCD, you're probably talking more XY. So how big can I get? How many parts can I fit on a single layer? And our largest build platform is going to be 292 by 163 by 410 millimeters. So really sizable, about 2 to 2.5 times larger than most DLP printers. So that again kind of speaks to the scalability of that technology.
And you guys are, I mean, I'll say as OEM, you're always innovating and pushing the boundaries of what you're doing with your equipment as well. So I think there's more to come. I think you've been around since, so you said 2016. So lots more innovation.
Oh yeah.
So I have someone asked about the some of the dielectric constants for these materials. I'll just give out another shout out for, if you go to Xometry.com and click on our solutions, you'll see under additive manufacturing LSPc, and you'll see a list of materials with their respective data sheets. So dielectric, for example, is you're probably going to be able to easily find that with the ESD materials, but you should be able to find some of that other information across the data sheets as well. So let me see. Is X Model 17 the best option for 3D printed molds for injection molding? If not, what do you suggest, Lewis?
Ooh, for injection molding, you have got out of this category of resins, I would probably suggest the X ceramic. The X ceramic with that high ceramic fill really holds that rigidity. You get really nice fine feature detail and surface finish on that part. And then similarly, because of that ceramic fill, you get a low coefficient of thermal expansion. So you're going to have that mold stay there. It's going to stay pretty stable through the injection molding process, and it'll be a reusable tool. We also have a freeform injection molding process, which if you're interested in, that's just direct printing of 3D printed tools. Feel free to shoot me an email about that, and I'd be happy to discuss that further with you.
Yeah, absolutely. Let me see, what do I have? Any limits on the largest part? So thinking about the platform size, any limits on largest parts or guidelines that you want to give them for how they should design based on build platform? I know sometimes I use like rule of 2 fingers, like something the size of a cantaloupe, that sort of analogy.
Yeah, I think coming from the Service Bureau environment, I say a lot of your limitations are limited by your application, meaning you could build a large part that takes up the entire build volume. It's going to print just fine. If you're looking for higher volumes of parts, I think your mention of somewhere in the neighborhood of like the 2-finger rule or something that's about the size or smaller than your fist always makes for a great production application with an additive. Or if you're looking at low volume production of really like maybe larger or highly complex or mass customized pieces, that all really makes the case for this as well.
Yeah, absolutely. I think this is a good question. So someone, Ian asks, how does support removal compare to other DLP processes? And mentions the challenge that they've had with other DLP platforms is parts warping because they're fighting gravity on the build. And I do want to first, I'll also say on my side, part of our manufacturing standards, because this is kind of a DLP process, what we call the upward facing layers, or if you imagine downward, if you're thinking about build tray, we tend to have slightly looser tolerances on that for 2 reasons. So we usually have the overall part tolerances, and then those upward facing layers tend to have a 10 to 20 thou plus or minus wiggle to that for 2 reasons. The first is support structure. There's nubs. So nubs will be removed, and there may be a manual sanding or something there that can affect tolerances. But also, as Ian mentioned, we have seen effects like that, similar to some DLP styles where that upward facing surface tends to have, I'm not going to call it a stretch, but it's compared to the rest of the naturally grown portion, has a little bit of a wiggle there.
Mm-hmm. Yeah, and I think that when you're looking at any sort of additive manufacturing as a service, you certainly have to account for that the trade-off on that is going through an iterative process, with the Xometry team, understanding that you might have to produce it more than once to kind of dial it in and get it the way that you want. It's, ultimately designing for the process. We see pretty decent, feature resolution, detail, and accuracy across the global geometry of the part. For those specific ones, as Greg mentioned, it might be surface dependent, or even you might look at like the material that you're using specifically for anything like that. If you're using a more rigid material, you'll probably, like the X ceramic, you'll see a little bit less of that.
Got it. And I have one last, I think I'll try to get to other questions offline, but I do have one last question, and Louis, you may be able to answer this as well. Across these materials, someone was asking about standards. I also saw something about FDA. Are there any highlights that you want to talk about on materials that have either compliance or skin sensitivity that are applications where you've seen one material shine over others? So say automotive application.
Yeah, so when it comes to I'll start off with, XABS is our most popular material for the same reason that ABS is one of the most commonly utilized plastics, in the world today, and that's because it's just a wonderful general purpose resin that can meet a lot of different functional requirements. And then you look at certifications like regarding the ESD capabilities of our resin with XESD. There's definitely some support for that. When it comes to biocompatible parts, we do have resins available for that. Not currently on Xometry.com, but we've got a lot of dental resins and FDA cleared resins available for those specific applications. Regarding skin sensitivity, for a fully cured part, you shouldn't have any issues. There's certainly opportunities to consult the safety data sheets for any of these resins. I'm sure you can get them through Xometry. If not, you can also get them just directly on our website. And it's always good if there's, particularly some people are more sensitive to a material than or chemical than others. And so you can always consult our SDS to look at the base materials and see if there's anything that you're concerned about. But a fully cured part really shouldn't have any issues.
Yeah, absolutely. And on that note, we have full staffed engineers in every field that we offer at Xometry. So any of those questions too, if you can't find that on our available resources online, just ask us. I know a guy named Lewis that will help answer that. But in all seriousness, we do our research as well, and depending on your application, we're very helpful and help engineering that's the sale and getting the most success out of your project. But thank you all so much, Lewis. Thank you so much for joining this. You are an expert in all fields. It's just really a pleasure to work with, and that's what I got.
Greg, thank you so much. It's been great speaking with all of you today, and also having the opportunity to share the virtual stage with you again. Feel free to connect with us directly or reach out online or via email or through the Xometry team. I think we've got what we feel is the best in resin 3D printing, and we're working with the best in additive manufacturing services. So give us a try, let us know what you think, reach out to us, and we're happy to hear what you think.
Thank you all. Have a great day.